Welcome in everyone. In this video we are going to discuss quadratics and how we can find solutions or number of real solutions algebraically when it comes to quadratics. So the first thing we're going to talk about is using our discriminant. So a quadratic function in standard form looks like y or f of x is equal to a times x squared plus bx plus c, where a, b, and c are all going to be either coefficients or constant values, where x determines what y is. Our discriminant is delta is equal to b squared, so whatever we have as our coefficient of our x term squared, minus 4 times our leading coefficient times our constant. So discriminant is equal to b squared minus 4ac. And what we're going to do is we're going to plug in these values for a, b, and c into our discriminant and see what our discriminant is. If our discriminant is greater than 0, then we will have two real solutions. Okay? A quadratic can never have more than two solutions. The fundamental theorem of algebra states whatever the highest degree of the function is, that's how many solutions it has. Our discriminant is how we look for real solutions. If our discriminant is equal to 0, then we are going to have one real solution. And then if our discriminant is less than 0, we are going to have no real solutions. Now notice I want to emphasize real here. We can still have non-real or imaginary solutions, but our discriminant is just looking at how many real solutions a problem has. Now, solutions can also be called roots, they can be called zeros or x-intercepts. So as we look at our example problem here, how many real roots or real solutions does the quadratic have below? So we're given y is equal to 2x squared minus 3x plus 5. So 2 is going to be our a, negative 3 is going to be our b, and 5 is going to be our c. And so we're going to take those values and plug them into our discriminant that we have above here. So our discriminant is going to be equal to negative 3 squared minus 4 times our a is 2 times our c is 5. So we would know that negative 3 squared is 9. Negative 4 times 2 times 5 is going to end up being minus 40. And so our discriminant is equal to negative 31. So therefore, we would have no real solutions. Okay? So if that answer ended up being a positive value greater than 0, we would have 2. If that value was equal to 0, we would have one real solution. So that's the beginning of our quadratics. We can also use our discriminant. If our discriminant ends up being a perfect square equal to 1, 4, 9, 16, 25, etc., then we know that a function is factorable, or that quadratic is factorable, which is going to lead us into our next part, which is solve by factoring. So whenever we're solving a quadratic, whether we have an equation where there is a term squared in it, or we have a function and we're trying to find its x-intercepts or its roots, the first thing we are going to need to do is set quadratic equal to 0. That way we can either solve it by factoring, which we'll show here in a second, or we can solve by the quadratic formula. The next step is we are going to want to factor out our greatest common factor, and I want to put if possible. Okay, because a lot of times factoring out that greatest common factor is going to make it a lot easier for us to either solve by factoring or solve by our quadratic formula. And the last one is solve by factoring. And then we may use zero product property. where we put both of our factors equal to 0 and then solve there. So we're given an equation, 6x squared plus 30x plus 18 is equal to negative 9x. So first thing we want to do is we want to set our quadratic equal to 0. Here we have most of our terms over here, but we have a negative 9x. So I'm going to go ahead and add 9x to both sides, making sure I add it to the like terms. So that's going to become 6x squared plus 39x plus 18 equals 0. So there's our first step. We're going to solve by factoring, set it equal to 0. The next is we want to see if we have a greatest common factor. And as we look at 6, 39, and 18, we notice a lot of times we want to see if everything's factorable by 2. Unfortunately, 39 is not divisible by 2, so we can't factor out a 2 from each term. However, we know 6 is divisible by 3. 3 plus 9 is 12, which is divisible by 3, so that number is divisible by 3. We know that. And then 1 plus 8 is 9, which would make it divisible by 3 as well. So I'm going to factor out a 3 from each of these terms, and it's going to look like this. We'd have 2x squared plus 13x plus 6 is equal to 0. And that's our factoring out of greatest common factors, if possible. And that's going to make our last step where we solve by factoring a whole lot easier, okay? Now, I'm gonna make sure I bring this 3 along with me. It's not gonna weigh heavily into the solution because we don't have an x term that we factored out, but I just wanna kind of bring it along to double check that, hey, I did factor everything out and I took everything into account. Because now what I'm really gonna focus on is what's inside here. So I'm gonna bring this 3, and the way we are going to factor this is a method I like to call guess and check. There's a whole lot of other methods you can find out. I like to go over some of the different ones in my class, but you can feel free to search all kinds of different methods solved by factoring on the internet. Now, the way I like to do guess and check is I focus on really the outside terms. Okay, I have 2x squared. The only 2 factors or 2 things I would multiply to get 2x squared are going to be 2x and x. So I know that the first terms in each of my binomials, one is 2x and the other one is x, because when I multiply the 2 of those, it gets me 2x squared. And then I'm going to look at 6, okay? And I'm going to think of the possible factors of positive 6 specifically. Okay, and because this middle term is positive, I know that both terms have to be positive. If I had a negative here, I would know I would have 2 negatives that multiply to get this positive 6, and they would add to be a negative number. But because this is positive and this is positive, I'm multiplying 2 positive numbers to get to this, and then we'll check to see what we have in the middle here. Okay, so I have 1 and 6 or 2 and 3. Let's just try 1 and 6. So I'm going to be plus 1 here, plus 6 here. And the way I'm going to check this is I'm going to do the OI of the FOIL method, and I'm going to multiply the outside 2. So 2x plus 6 is 12x. 1 times x is going to be 1x. And if I add those together, that 2x times 6 is 12x plus 1x. If I add those together, give me 13x. Then I know I have factored it successfully. Okay, and then the last step is our zero product property, which I'm going to take all of the factors or all the things being multiplied together that have x in them, set them equal to 0, and then solve. So I have this 2x plus 1. So I'm going to take that 2x plus 1, set it equal to 0, solve for x. So x is going to be equal to, because I'm going to divide by 2 on both sides, negative 1 over 2. And then when I have x plus 6 is equal to 0, I know that my x equals negative 6 is going to be the solution. And you can do this a variety of different ways. You can write out as x equals negative 1 over 2 and x is equal to negative 6. Sometimes you may see it written as x equals negative 6 comma negative 1 over 2. All right? Our next method is going to be our quadratic formula. So much like our discriminant had to use A, B, and C to plug things in, quadratic formula does the same thing. X is equal to the opposite of B plus or minus the square root of B squared minus 4AC. Notice inside here, that's our discriminant. So that's why when we looked at our discriminant, okay, if you think about the values underneath the radical, if we can square root a positive to get two different solutions because the square root would be plus or minus, which is that plus or minus right there. If we had 0, well, the square root of 0 is going to be 0. And if we add or subtract a 0 from something, it's not going to change. So we won't get the kind of two roads we get in a quadratic. But if we have a negative under here, we can't square root a negative number and get a real value. So that's why we have no real solutions if our discriminant is less than 0. So kind of tie that back. So again, when we are doing quadratic formula, we need it in standard form. We need our equation equal to 0. So if we solve for x here, I've got 6x squared minus 2 is equal to 8x. I'm going to work to get this equation equal to 0. So I'm going to subtract 8x on both sides. I don't have an x term here, so this is just going to become 6x squared minus 8x minus 2. And so from there, we're going to use our quadratic formula. I'm going to say x is equal to the opposite. Our b is negative 8 here. Let me go ahead and mark all these. So I have a, b, and c right there. So the opposite of negative 8 plus or minus the square root of negative 8 squared minus 4 times 6 times negative 2 all over 2 times 6. So I'm going to work to simplify this. The opposite of negative 8 is just going to be that positive 8 plus or minus the square root of 64 minus, let's see, that's going to be, or no, that's going to be a negative times a positive times a negative, so that would be plus 4 times 6 would be 24, times 2 would be 48, all over 12. And so we have 8 plus or minus the square root of, that's going to be 112, oops, 12, all over 12. Okay, so now from here, because we are asked to keep it as simplified radical, and I wrote that on the wrong one, I should have wrote it on this one. As a simplified radical, I need to simplify this square root of 112 right here. Okay, so I know I'm going to use some prime factorization, or I can see what's the biggest perfect square I can divide out of 112. Well, I know 112 is divisible by 4. So we're just going to divide 112 by 4, and we get 4 and 28. Okay, and then 28 is also divisible by 4. So we know 28 would be 4 and 7. So really we can think of 112 as the square root of 4 times square root of 4 times square root of 7. Because 4 times 4 times 7 will give us 112. And since 4 is a perfect square, that means this is going to be 2, 2, and the square root of 7 is going to stay underneath there. So I have 8 plus or minus 2 times 2 would be 4, square root of 7 over 12. And I can simplify this even farther because I know 8, 4, and 12, it has to be here, here outside of the radical, and underneath have to all be divisible by the same thing. So this is going to simplify to be x is equal to 2 plus or minus the square root of 7 over 3. And that would be our solution left as a simplified radical. And we can just leave it like that because that's 2 plus square root of 7 divided by 3 as well as 2 minus the square root of 7 divided by 3. Now, if it wanted you to give an approximate answer, you would just put 2 plus square root of 7 divided by 3 in your calculator as well as 2 minus the square root of 7 divided by 3 in your calculator. And those would be your approximate answers. So our last challenge question we're going to kind of go through is, let's say we are given a function f of x is equal to x squared plus kx plus k plus 3, and we want to find the value of k so that f of x has one real root. So normally when we have quadratics, we don't have two variables, but we're told this function is based off x. So what's happening here is this function can be an infinitesimal amount of different functions based off what k is. But we want to find out what k would be if this up above only had one real root. Well, if we think back to our discriminant, okay, we only have one real root when our discriminant is equal to 0. So what we're going to do is we're going to find the discriminant of this function and set it equal to 0. And so I know my a is going to be 1. My b is going to be this k, because k is a constant value. Okay, we don't know what k is. Okay, it can be anything, but we want to find out what k would have to be for there to be one real root. Now, because there's no other x terms here, and I have a k and a 3, our c is essentially going to be k plus 3. It's going to be this whole constant term. Remember how I said k is a constant? And c is going to be this binomial, essentially. Okay, and so we know our discriminant is equal to b squared minus 4ac. And we know that b is k. So we have k squared minus 4 times 1 times k plus 3. Okay, now, again, I want to go back to, we know it has one real root, or we're looking for what k has to be for this to have one real root. So I know my discriminant has to be 0. So I'm going to multiply everything out. I'm going to have to distribute this -4 to k and positive 3. So I have 0 is equal to k squared minus 4k minus 12. Okay, and so because it's written this way, I want to find out, I'm solving for k. K ends up being k squared here. I now have a quadratic equation with one variable. I'm going to go ahead and try and factor this. Okay, my equation is already equal to 0, so I can start factoring. I don't have any greatest common factors here. So I'm essentially going to skip right to step 3, k and k, because the only two things I can multiply together to get k squared is k and k. Now, I'm looking for, at my last term, I have a -12 here, so I know one of my constants in the binomials has to be negative, one has to be positive. Because the only way I can multiply two numbers to get a negative, one has to be positive, one has to be negative. Because my leading coefficient is 1, I can kind of cheat a little bit here, and I know that the bigger number has to be negative, because when I combine them, I'm going to have more negatives than positives. Okay, so if I think about the numbers that multiply to get -12, I've got 1 and -12, 2 and -6, 3 and -4, and then vice versa for all of those. And I need them to have a difference of 4, so I know +2 minus 6 would be my 2. So if I multiplied 2 times -6, that would give me that -12. K times -6 is going to be -6k. 2 times k is going to be 2k. I combine them, I get -4k. So k has to be equal to -2 and 6. So the values for k that would make f of x have only one real root are going to be -2 and +6. And sometimes they may make some stipulations so that k is greater than 0. In that case, you know that 6 would be your only option, or if k is less than 0, -2 would be your option. Okay? So that's going to cover it for our algebraic solving of quadratics. Hopefully this was a good little reminder review for you, and I'll see you all in the next one.